Okay, 2.54 gives us the transfer matrix, which is the exact same as sort of the scattering matrix from 2.53, with the only difference being that instead of being sort of in terms of B and F and A and G, this one's in terms of F and G and expresses in terms of A and B. So in part A, our first goal is to rewrite this this transfer matrix M in terms of the elements of the scattering matrix S. So, for reference, our two equations of interest are BF, expressed in terms of the scattering matrix S11, S12, S21, S22, multiplied by AG. And then we have our transfer matrix, which is going to express F and G in terms of the matrix M11, M12, M21 and M22, and this time in terms of AB. So in this case, our actual, if we wanted to actually rewrite everything in sort of a the format of like an actual system of equations, we would write, okay, B is equal to S11A plus S12G, and then F is equal to S21A plus S22G. Similarly, on the right, we have F is equal to M11A plus M12B, and then G is equal to M21A plus M22B. So our primary goal, our first goal, is to find the four elements of the M matrix in terms of elements of the S matrix. So this is our S matrix. Our goal then is to convert this into an M matrix. So what that means is we want to rewrite this system of equations. Instead of using B and F, we want to do it in terms of F and G. So to do that, we can recognize that G is going to then equal 1 over S12 times B, subtracted by S11 over S12 times A. So what I've done is I've taken this first expression and I've isolated G. So in that case, if that's true, then I can plug this expression back into G for the second expression, and what I get is F is now equal to S21A plus S22 times 1 over S12B minus S11 over S12A. So F, therefore, is equal to S21A plus S22 over S12 times B minus S22 S11 over S12 times A. Or, writing it in a slightly neater way, we get F is equal to, let's see, S2, I'm going to combine these two into a single fraction, so this is going to become S21 S12 minus S22 S11 divided by S12 multiplied by A plus S22 over S12 multiplied by B. Is that correct? Yes. Yes, that is correct. Okay, and then similarly for above, we already have G. G is equal to 1 over S12 times B minus S11 over S12 times B. Or times A, sorry. Or if I want to write, actually I should probably write this around, reverse this just to make it symmetrical. In which case, this is going to give us negative S11 over S12 times A plus 1 over S12 times B. Okay, so now, at this point, what we've done basically is we've taken this original system, which is in terms of sort of this scattering matrix, and we've rewritten it in the form of sort of FG equals AB. Because if we look here, originally we have B and F in terms of A and G, and now we've rewritten it, so now we have F and G in terms of A and B. This is the form of a scattering matrix. This can be rewritten then as FG is equal to the matrix S21, S12 minus S22, S11 over S12. And then we have S22 over S12. And then we have negative S11 over S12. And then we have 1 over S12. And this is getting multiplied by the vertical matrix AB. So this is, therefore, our M matrix in terms of S. And with that, we are finished with the first half of this problem. The next part, then, is to do the same thing with this and effectively pretty much take this and rewrite it in terms of B and F. So in that case, if we want to do that, I can immediately say, okay, well, let's see. If we want to rewrite this from F and G into B and F, I can immediately say, well, B, by taking the second expression here, by taking this expression, I can say B is equal to 1 over M22 times G minus M21 over M22 times A. And realistically, I should probably reorder this. So B is actually equal to negative M21 over M22 times A plus 1 over M22 times G. And now I plug this into the F term, which means that F is now equal to M11 times A plus M12 multiplied by negative M21 over M22 times A plus 1 over M22 times G. And at this point, F then equals, let's see, M11 times A minus M12, M21 over M22 times A plus M12 over M22 times G. Combining the A's into a single fraction, we get F is therefore equal to M11, M22 minus M12, M21 over M22 plus M12, oh, and I forgot the A here, M12 over M22 multiplied by G. And now that I have this, I can rewrite everything. So now my two expressions are B, this B expression, and then I have this F expression. So I've done pretty much the same thing here, but I've done it in the opposite direction, and now I have an expression of B and F in terms of A and G. So writing this as a writing this as a scattering matrix now, we get BF is then equal to negative M21 over M22, 1 over M22, and then M11, M22 minus M12, M21 all over M22, and then M12 over M22. And this is all multiplied by the vector AG. Let me just double check that that is in fact correct. 1, 1, M22 minus M12, M21, M22. Yeah, so this is our scattering matrix in terms of the M matrix components. Finally, we want to express the reflection and transmission coefficients for a particle incident from the left and to the right, respectively, in terms of elements of the M matrix. So for that, we just have to look at sort of our new scattering matrix in terms of the M matrix elements, which is right here. And we can recognize, okay, if we have scattering from the left and transmission from the left, in this case, the particle is coming in from the left, which means that the G term is going to be 0. So in that case, reflection is just going to be equal to this term, and transmission is going to be equal to this term. So RL is going to be equal to the magnitude squared of negative M21 over M22 squared. Because remember, when we have left transmission, in this case, G is equal to 0. So our new two formulas from this top matrix is going to be B is equal to negative M21 over M22 times A. And then we have F is equal to M11 M22 minus M12 M21 over M22 times A, because the G term is always 0, so these two terms don't matter. So because of that, reflection is going to be the ratio between A and B, and then transmission is going to be a ratio between F and A. So transmission from the left is then therefore equal to the magnitude of M11, M22 minus M12, M21 over M22 magnitude squared. Similarly, if we have reflection from the right and transmission from the right, this means that A is now equal to 0. So we have the opposite case, where now it's this term and this term that matters. So by the same logic, reflection from the right is going to equal, let's see, B is equal to, so our two expressions are going to be, B is equal to 1 over M22 times A, I believe. 1 over M22 times A, yeah, and then, or sorry, not A, G, because A is equal to 0. And then we have F is equal to M12 over M22 times G. So remember, our particle comes in from G, so that means F is going to describe the reflection. So reflection is going to be equal to the magnitude squared M12 over M22 squared, because since the particle is coming in from the right now, the F term is what's going to determine the relative amplitude of the reflected transmission, and in contrast, the B term is going to be what determines the transmitted amplitude. So transmission from the right is going to be equal to the magnitude of 1 over M22 squared. And with that, we are done with part A. Okay, so in part B, we have a potential that consists of two isolated sort of non-zero pieces, M1 and M2, and then we have these three swaths of sort of empty space in between. So we want to show that the M matrix, aka the scattering matrix, or sorry, not the scattering matrix, the transfer matrix for the combination is just the product of the two individual transfer matrices for each section separately. So to do this, first off, recognize that the general form of the wave function is going to be, you know, on the far left we have a e to the ikx, and then we have a reflected term, b e to the negative ikx. In the middle here, we have something that we don't care about because it's determined sort of by the M matrix. In the middle, we have, you know, f e to the ikx, and then reflected back, we have g e to the negative ikx, and then finally to the right, what's two other letters? Let's say c e to the ikx, and reflected back dE to the negative ikx. So this is the general form of the wave function, and in the middle, in these M1 and M2 regions, we have some other random psi, let's call them psi1 and psi2, but we don't really care about that, because what we're caring about is the sort of transmission matrix. So that basically is going to include psi1 inside of it, and it's going to determine F, G, A, B in relative to each other for us. So now let's recognize what the transfer matrix is actually written as, because remember, transfer matrix, what it does is it gives us sort of the amplitudes to the right in terms of the amplitudes to the left. So if we wanted to write out the equation for the transfer matrix in both of these regions, we would get, okay, F and G is going to equal the transfer matrix in region 1 in terms of A and B. Similarly, for region 2, we have C and D can be written in terms of the transfer matrix in region 2, and then expanded in terms of F and G. So you might realize that we can do sort of a little bit of substitution here, because F and G is something that we share, and we recognize that F and G is equal to M1 AB. So that means CD is now equal to M2 times, and then if we substitute FG with this expression, then we get M2 times M1 times AB. So that means CD is now equal to M2 M1 times AB. Recognize that, you know, C and D is all the way to the right and A and B is all the way to the left. Therefore, our matrix multiplication thing has gone through. The combined sort of transfer matrix from going from all the way to the left to all the way to the right is now just the product of M2 and M1. And with that, we have finished this part of the problem. Okay, in part C, we want to construct the M matrix, but this time for the Dirac delta potential. So we've already done this many times in earlier sections. We know the general form of the wave function takes on the form of a free particle to the left and a free particle to the right. Then we stitch this together by enforcing continuity conditions, recognizing that the wave function has to be continuous at x equals a, and then recognizing that the derivative is discontinuous because of the fact that the potential goes to infinity at x equals a, and therefore creating this bottom equation. So if you're not familiar with this whole process, please go back and look at the section regarding infinite delta wells. I believe it was 2.5. But regardless, at this point, our goal then is to find the M matrix, and to do that, recognize that we have to solve f and g in terms of a and b. So immediately, what I see here is I can do a substitution. I can take this expression and substitute it into this expression. So if I do that, and I'm going to do it in red, I get ik times f e to the ika minus g times e to the negative ika. And this is subtracted by ik times a e to the ika minus b times e to the negative ika. And this is going to be equal to negative 2m alpha over h bar squared. I'm replacing this with f e to the ika plus g times e to the negative ika. And at this point, I can do a little bit collecting of terms, and I get f e to the ika, ik plus 2m alpha over h bar squared, and then added with ge to the negative ika, multiplied by negative ik this time, and then added once again with 2m alpha over h bar squared. This is going to equal, I'm going to move this term right here to the right, and I get ik a e to the ika plus, or not plus, minus b e to the negative ika. So at this point, then I collect a little bit more, and I get f e to the ika times ik h bar squared plus 2m alpha over h bar squared. And I'm going to solve for f first. So this is going to be equal to ik times a e to the ika minus b e to the negative ika, subtracted by g e to the negative ika, multiplied by negative ik h bar squared plus 2m alpha over h bar squared. Then I take the reciprocal of this, and I get f e to the ika is going to equal ik h bar squared over ik h bar squared plus 2m alpha, multiplied by a e to the ika minus b e to the negative ika. Is that correct? Ik h bar squared plus 2m alpha. Yeah. And then we are subtracting by g times e to the negative ika, and then the two h bars cancel out. We get negative ik h bar squared plus 2m alpha divided by positive ik h bar squared plus 2m alpha. And then now I take this fe to the ika and I substitute it back into the top expression. I'm going to write this in blue. So what I get is a e to the ika plus b e to the negative ika is going to equal g e to the negative ika plus f e to the ika, which I'm going to substitute with this. So plus ik h bar squared over ik h bar squared plus 2m alpha times a e to the ika minus b e to the negative ika, and then subtracted by g e to the negative ika, multiplied by negative ik h bar squared plus 2m alpha over ik h bar squared plus 2m alpha. And at this point, I can do a little bit of term combination once again. I get g e to the negative ika times 1 minus negative ik h bar squared plus 2m alpha over ik h bar squared plus 2m alpha. Is that correct? 1 minus that, yeah. And then this is going to equal a e to the ika using distributive property, 1 minus ik h bar squared over ik h bar squared plus 2m alpha, and then plus be to the negative ika. This time it's going to be 1, let's see, the other one was minus, this one is going to be plus ik h bar squared over ik h bar squared plus 2m alpha. Combining all these fractions together, I get ge to the negative ika is multiplied by ik h bar squared plus 2m alpha, and then plus ik h bar squared minus 2m alpha, divided by ik h bar squared plus 2m alpha. This is going to equal ae to the ika multiplied by ik h bar squared plus 2m alpha minus ik h bar squared, which is going to be 2m alpha over ik h bar squared plus 2m alpha, plus be to the negative ika, and this is going to be 2 ik h bar squared plus 2m alpha over ik h bar squared plus 2m alpha. Okay. Immediately I see that these two terms cancel, and I get ge to the negative ika multiplied by 2 ik h bar squared over ik h bar squared plus 2m alpha. And actually, I'm just going to straight up cancel the e to the negative ika right away. This is going to give me ae to the 2 ika times 2m alpha. At the bottom, ik h bar squared plus 2m alpha. And then plus the e to the negative ik in front of the b cancel, we get b to ik h bar squared plus 2m alpha over ik h bar squared plus 2m alpha. Okay, now we just got to move everything over. So g on its own is therefore equal. Everything at the bottom cancels out. What we're left with is ae to the 2 ika multiplied by, the 2's canceled out, we get m alpha over ik h bar squared. Is that correct? Yeah. And then plus b, and then this is going to be, the 2's cancel out, once again we get ik h bar squared plus m alpha divided by ik h bar squared. So at the end of the day, let's see, just to make this a little bit, let me just double check that this is correct. This is going to be m alpha e to the 2 ika over ik h bar squared. Yeah, this one's right. And then on the other side, ik h bar squared should be multiplied by I over I. That is going to be, yeah, okay, that seems correct. And now let's plug this back into f and solve for that. Okay, so now let's plug this back into the f expression, which I'm going to take from up here. Erase this stuff on the side. There we go. Okay, so now f e to the ika is going to equal the same thing at the front, ik h bar squared over ik h bar squared plus 2m alpha times a e to the ika minus b e to the negative ika. And then we're subtracting, this time, let's see, negative ik h bar squared plus 2m alpha over ik h bar squared plus 2m alpha, and then ge to the negative ika. So I'm going to just put the e to the negative ika into everything. This is going to give me a e to the ika times m alpha over ik h bar squared, and then added with b e to the negative ika. Whoops, forgot the parentheses. Ik h bar squared plus m alpha over ik h bar squared. Close everything off with a bracket f e to the ika is then going to equal, God, okay, this is a disgusting equation. A e to the ika, let's see, ik h bar squared over ik h bar squared plus 2m alpha, and then subtracted by negative ik h bar squared plus 2m alpha over ik h bar squared plus 2m alpha, and then multiplied by m alpha over ik h bar squared. Is this correct? Stuff at the front, that's right, and then subtracted by everything at the all this crap at the back. Yeah. Okay, and then we're adding b e to the negative ika, and this is going to be, let's see, negative ik h bar squared over ik h bar squared plus 2m alpha. And then at the right, we're going to be subtracting by negative ik h bar squared plus 2m alpha over ik h bar squared plus 2m alpha. Multiplied by ik h bar squared plus m alpha over ik h bar squared. Okay. I'm just going to take this as a chance to get rid of the e to the ika in front of f. So this is going to give me a multiplied by, let's see, multiply everything by ik h bar squared. This gives me negative k squared h bar fourth plus ik h bar squared m alpha minus 2m squared alpha squared over ik h bar squared plus 2m alpha times ik h bar squared. And you know what, actually it might be a better idea not to distribute out everything right away, so I'm not going to do that right now. I'm going to combine this first. So in that case, we're multiplying everything by ik h bar squared, so ik h bar squared squared minus negative ik h bar squared plus 2m alpha, and then multiplied by m alpha. And this is getting added to b e to the negative ika times, let's see, ik h bar squared, once again, negative ik h bar squared squared subtracted by negative ik h bar squared plus 2m alpha times ik h bar squared plus m alpha, and then all of this is divided by ik h bar squared plus 2m alpha times, and this is supposed to be a negative 2 ika, my apologies, ik h bar squared plus 2m alpha multiplied by ik h bar squared. Is that correct? Negative ik h bar squared squared, and then at the bottom it's ik h bar squared plus 2m alpha times ik h bar squared subtracted by negative ik h bar squared plus 2m alpha, ik h bar squared plus m alpha. Okay, yeah, that seems correct. And now we have to simplify this mess of an expression. So let's see here. What can I do to make this a little bit easier on myself? Give me 1 second to look through this problem. Okay, yeah, this is not a very fun simplification, so let's go through this one step at a time, starting with a, which I'm going to do in green. So this top expression is going to simplify to ik h bar squared squared plus ik h bar squared m alpha plus 2m squared alpha squared. Is that correct? No, that's supposed to be a minus. So ik h bar squared squared plus ik h bar squared m alpha, and then minus 2m squared alpha squared. Yep. And then this at the bottom is ik h bar squared plus 2m alpha multiplied by ik h bar squared. Now, immediately when I look at this, I'm tempted to say that I can somehow turn this into a binomial, because this is some sort of polynomial where ik h bar squared is sort of the substitute for like an x variable, and this format seems to just suggest that I can get something of the form of ik h bar squared plus 2m alpha multiplied by something else. So if I look at this, you know, if I say that, okay, one of the terms of this double binomial is going to be ik h bar squared plus 2m alpha at the top, multiplied by some other thing. So obviously the first term has to be ik h bar squared, because that's the only way to get this ik h bar squared term. But this second term and this third term. So this seems to just suggest that I should do a minus m alpha, because if I do a minus m alpha, then the last term becomes minus 2m squared alpha squared. The middle terms then become negative ik h bar squared m alpha plus 2 ik h bar squared m alpha, which does indeed cancel out to 1 ik h bar squared m alpha. So this is a correct binomial substitution. At the bottom, I'm going to get ik h bar squared plus 2m alpha, just like before, multiplied by ik h bar squared. So instantly these two terms cancel out, and I'm left with ik h bar squared minus m alpha over ik h bar squared, which is much nicer compared to before. This next expression, let's do in blue. So I have negative ik h bar squared squared, and then if I multiply this out fully, then I get, let's see, minus, you know what, actually, instead of doing that this way, I'm going to pull out the two subtraction terms. I'm going to say that this becomes a positive, and this negative comes out, and this positive becomes a negative. That way, my mental math takes less of a strain when I'm doing this. So in that case, I get ik h bar squared squared, and then at the front I'm going to get minus ik h bar squared squared, and then let's see, minus ik h bar squared m alpha plus 2 ik h bar squared m alpha plus 2m squared alpha squared, and at the bottom I get ik h bar squared plus 2m alpha times ik h bar squared. Once again, these two terms cancel out. The top term becomes ik h bar squared m alpha plus 2m squared alpha squared, and then the bottom becomes, it stays the same, ik h bar squared plus 2m alpha multiplied by ik h bar squared. Now immediately here I see I can distribute out an m alpha, so I get ik h bar squared plus 2m alpha at the top multiplied by m alpha, and at the bottom I get ik h bar squared plus 2m alpha multiplied by ik h bar squared. These two terms instantly cancel. I get m alpha over ik h bar squared. So now my f term is f is equal to a times, let's see, the green expression, which is going to be ik h bar squared minus m alpha over ik h bar squared. And then I'm going to be subtracting by b e to the negative 2 ika. Is that correct? Yeah. And then multiplied by m alpha over ik h bar squared. Remember, we're trying to get f and g. We already solved for g, so let's move that down. And therefore, we now have our scattering matrix, or transfer matrix. My apologies, I keep on mixing these two up. This is going to give me, I want color 1 to be, there we go. Our M matrix, therefore, is going to equal, at the top, ik h bar squared minus m alpha over ik h bar squared, and then negative e to the negative 2 ika times m alpha over ik h bar squared. At the bottom left, we get e to the 2 ika times m alpha over ik h bar squared. And then to the right, we get ik h bar squared plus m alpha over ik h bar squared. Now, note here the difference between the M matrix and sort of the S matrix, because when we're dealing with the scattering matrix S, when we had a symmetric potential, what we saw was that the diagonal terms were all equal. In this case, because the M matrix is not is dealing with the right side amplitudes with respect to the left side amplitudes, even though the potential is symmetric, it no longer has sort of same elements across all of the diagonal terms. The M matrix instead has something that does look symmetric still. It's just like symmetric with respect to a change in sign. Now, the actual sort of significance behind this kind of stuff is going to get covered much more in Chapter 3. So for now, we're just going to sort of leave this as a very interesting observation and sort of leave it at that. Anyway, now we can move on to Part D. Right. Finally, in Part D, we are given a double delta well. And in this case, we're asked to solve, once again, the M matrix for the entire system. So if you think back onto Part B, you should remember that in the case where we have a double delta, in a case where we have basically two potentials in two different localized areas, the net M matrix is going to be found by taking the individual M matrices and multiplying them together. So if we recognize that, this is our first delta well, and this is our second delta well, and everywhere in between is 0, and then we recognize that this is M1, and this is M2, and this is at x equals positive a, and this is at x equals negative a. Then from Part B, we know that the total M matrix, which is the combined transfer matrix for this entire system, is going to be the product of M2 times M1. So we already know what M2 is from up here. This is M2. So I'm just going to take this and copy it over. And M1, well, that's just the delta well again, but located at x equals negative a instead. So M1 is going to be the exact same thing, but with all the a's replaced with negative a's. So ik h bar squared minus m alpha over ik h bar squared, and then negative e to the, this time, 2 ika instead of negative 2 ika times m alpha over ik h bar squared. On the opposite side, e to the negative 2 ika instead of positive times m alpha over ik h bar squared. And then finally, ik h bar squared plus m alpha over ik h bar squared. And now this is the part where it's really, really easy to mess up. Thankfully, we've written everything out, so we shouldn't mess up. But sort of the thing that really causes a lot of trip ups here is that a lot of people forget, especially if you're just starting linear algebra, that matrix multiplication is not commutative. So M2 times M1 is actually not the same thing as M1 times M2. So we specifically showed that the combined M matrix has to be M2 times M1, with M2 on the left and M1 on the right. So you cannot mistake this, and you cannot do it in the opposite order, because if you do that, you will get a wrong answer. So the combined matrix is going to be M2 times M1, and this is going to be a very messy thing. So let's see. Give me 1 second to check through my work, and then we will resume. Right, actually, because of how complicated this matrix is going to be to solve, I think I'm going to do this individually part by part. So this is going to be M11, M12, M21, M22. I'm going to start with M11. So that's going to be M11 is going to be this row multiplied by this column. So to do that, we're going to get, let's write it to the right here since we have space. M11 is going to equal, let's see, ik h bar squared minus m alpha over ik h bar squared because it's this first term times this first term, and then added with this second term times this first term. So that is going to give us minus e to the negative 4 ika times m alpha over ik h bar squared squared. And then, let's see, there should be a few things that we can cancel out. So immediately, I see that I can, the immediate thing I see is that these two fractions share the same denominator. So I can combine everything and I get, let's see, negative k squared h bar fourth at the bottom. And then at the top, I'm going to get ik h bar squared minus m alpha squared minus e to the negative 4 ika times m squared, and you know what, I'm not even going to use parentheses, times m squared alpha squared. And then at this point, let's see, is there any way that we can simplify this a little bit more? Squared. Not really. So at this point, this is our M11. Now let's move on to M12, which we'll do in blue. Okay, M12 is going to be this first row up here multiplied by the second column down here. So this is going to give us a cross product. Let's see. Ik h bar squared minus m alpha times ik h bar squared, or divided by ik h bar squared, multiplied by negative e to the 2 ika times m alpha over ik h bar squared, and then plus ik h bar squared plus m alpha over ik h bar squared times negative e to the negative 2 ika times, m alpha over ik h bar squared. Once again, immediately I see that there's a common denominator here. So this is going to be divided by negative k squared h bar fourth at the bottom. Then at the top we have ik h bar squared minus m alpha times negative e to the 2 ika. And my fraction is getting very lopsided. I apologize for that. And then we're adding ik h bar squared plus m alpha times m alpha times e, or another negative. Oh my god. Okay, I am running out of space. Give me 1 second. Let's expand my width to 2000, expand my height to 20,000. There we go. Go back to brush, multiply by negative e to the negative 2 ika. Okay, so immediately there's negatives that can cancel out. So, and then also I can factor out an m alpha. So m alpha over k squared h bar fourth, and this is going to be multiplied by ik h bar squared minus m alpha times e to the times e to the positive 2 ika, and then plus ik h bar squared plus m alpha times e to the negative 2 ika. And let's see. Yep, that seems about right. Okay, now we move on to the third element of the matrix. So term 3, let's do in purple, M21. That's going to be, let's see, going to be this row multiplied by this column. So that's going to give us M21 is going to equal, and you know what, actually I'm going to take a picture of this and move it off to my second monitor, just so I have a frame of reference. Okay, this is going to give us, let's see, ik h bar squared minus m alpha over ik h bar squared as before, and then this is being multiplied by e to the 2 ika times m alpha over ik h bar squared. and then plus ik h bar squared plus m alpha over ik h bar squared, and then multiplied by e to the negative 2 ika times m alpha over ik h bar squared. So once again, common denominator. At the bottom, it's going to be negative k squared h bar fourth. And then at the top, we have m alpha times ik h bar squared minus m alpha times e to the 2 ika. And then we are adding ik h bar squared plus m alpha times e to the negative 2 ika. And that is our third element, and now we move on to our final. The final term, let's do in green. So the final term, m22, is going to be this bottom row and this rightmost column. So that's going to give us, let's see, negative e to the 4 ika times m alpha over ik h bar squared, I believe, yeah. And then added with ik h bar squared plus m alpha over ik h bar squared. So once again, common denominator, negative k squared h bar fourth. At the top, we have negative e to the 4 ika times m squared alpha squared plus ik h bar squared plus m alpha squared. And I don't believe there's really that much else we can do with this other than just maybe flip the terms around, get rid of the cancellations, cancel some negatives, so we have e to the 4 ika m squared alpha squared minus ik h bar squared plus m alpha squared over positive k squared h bar fourth. So now that we're done with this, we just plug everything into our final matrix. So m is equal to a very long convoluted thing, and I'm just going to copy paste each individual term in. So starting with m11, and you know what, we can make this a little bit, we can get rid of the negatives, clean this up a little bit. This is actually equal to e to the negative 4 ika m squared alpha squared minus ik h bar squared minus m alpha squared over positive k squared h bar fourth. So I'm going to delete this and substitute this, which is a slightly neater expression in. And then m12 is going to be in blue, this expression. And maybe I want to clean this up a little bit as well. So I'm going to rewrite this just so everything's in the same form. M alpha multiplied by ik h bar squared minus m alpha times e to the 2 ika plus ik h bar squared plus m alpha e to the negative 2 ika. Close this off and then divide everything by k squared h bar fourth. Delete this expression and substitute it in with this. Okay, now m21 looks very similar via the diagonal symmetry, and we are running out of space, so we actually have to move stuff over a little bit like this, and there we go. And then m22 is this. And then we close everything off. Okay, so this is our combined M matrix. It's a very messy expression, but it's correct. So the next thing we're asked to do is to find the transmission coefficient for this potential. And remember from part A, we're actually given this. Way back in part A, we found the transmission coefficient in terms of M matrix elements. And what we found was that transmission from the left and transmission from the right were equal to this and this respectively. Now, For the purpose of just making my life a little bit easier, I'm going to find transmission assuming that the particle is incident from the right instead of particle incident from the left. If you want to find T sub L, by all means plug it in and find this horrible expression, but I really don't want to do that. So just to make my life easier, I'm going to solve for TR. So if we solve for TR, then what we're going to find is that the transmission coefficient given an incident particle from the right is going to equal 1 over m22 magnitude squared. And here's actually, in this case, it turns out to work out very nicely because this is actually going to turn out to be equal to m11 times m22 minus m12 m21 over m22 magnitude squared, which is the transmission coefficient from the left in this case. Because remember, this potential, this double delta well, is symmetric with respect to x equals to 0. So what that means is that regardless if our particle is from the left or coming in from the right, the transmission coefficient and the reflection coefficient both have to be equal. So in this case, it doesn't actually even matter. So why not just use the simpler one? So let's do this. M22 is equal to E4IKA m squared alpha squared minus IK h bar squared plus m alpha squared over k squared h bar fourth, and then the complex conjugate of m22 is going to be e to the negative 4 IKA times m squared alpha squared minus negative IK h bar squared plus m alpha squared divided by k squared h bar fourth. So our final step now is to find the magnitude squared of this expression and then find TR. All right, multiplying this is going to be horrible, so let's just do it. Magnitude m22 squared is going to be, oh god, okay, e to the 4 IKA. Well, you know, I don't even know why I'm writing this out fully when I have both terms. So term 1 times term 1. That one's simple enough. That's m fourth alpha fourth. And then we're going to be multiplying term 1 by term 2. So that's going to be minus E4 IKA m squared alpha squared times negative IK h bar squared plus m alpha squared. Term 2 times term 1 is going to be minus e to the negative 4 IKA times m squared alpha squared. And then multiplied by IK h bar squared plus m alpha squared. And then the final term is going to be plus IK h bar squared plus m alpha squared times, whoops, there we go, times minus IK h bar squared plus m alpha squared. And this whole thing is then divided by, thankfully the denominator is simple, k fourth h bar 8. Okay, so immediately you should notice that even though we're taking the magnitude squared here, we're getting complex exponentials. So that obviously isn't correct. And the reason why this is happening is because we have to re-express this in terms of cosines and sines. So remember that trig identities can be, or trigonometric functions can be related to complex exponentials. So let me pull up my table. Functions to complex exponentials. And what we find is cosine of x is equal to e to the ix plus e to the negative ix times 1/2, and sine of x is equal to e to the ix minus e to the negative ix to the power of 1/2. So evidently we're going to have to express out everything fully before we can actually find out what the terms here are. So m22 magnitude squared is going to equal, m fourth alpha fourth minus e to the 4 IKA m squared alpha squared. And you know what? Actually, I'm going to combine the middle two terms just to make my life a little bit easier. So I'm going to be subtracting m squared alpha squared in both cases, and then e to the 4 ika times negative ik h bar squared plus m alpha squared plus e to the negative 4 ika times ik h bar squared plus m alpha squared, and then finally plus ik h bar squared plus m alpha squared times negative ik h bar squared plus m alpha squared. And then all this is once again divided by k fourth h bar eighth. So I'm going to solve for this inner term first. I'm going to do this in red. So let's see, this is going to be e to the 4 ika times, what is this going to give me? Two negatives make a positive, but two i's make a negative. Negative k squared h bar fourth minus 2i k h bar squared m alpha plus m squared alpha squared, and then plus e to the negative 4 ika multiplied by negative k squared h bar fourth, and then this time plus 2i k h bar squared m alpha, and then plus m squared alpha squared. From this point, let's see. At this point, I can start combining some like terms, because this is going to give me e to the 4 ika negative e to the 4 ika k squared h bar fourth minus e to the 4 ika times 2i k h bar squared m alpha plus e to the 4 ika m squared alpha squared plus e to the negative 4 ika, or in this case subtracted by k squared h bar fourth plus e to the negative 4 ika 2i k h bar squared m alpha, and then plus e to the negative 4 ika m squared alpha squared. So there's a few like terms here. So immediately negative k squared h bar fourth multiplied by e to the 4 ika plus e to the negative 4 ika. That combines this term and this term. Next off, plus 2i k h bar squared m alpha multiplied by e to the, let's see, instead of doing that, I think I want to add to distribute out the negative, in which case e to the 4 ika minus e to the negative 4 ika. This cancels out this term and this term, and then finally plus m squared alpha squared e to the 4 ika plus e to the negative 4 ika. So then, using our trigonometric conversion to complex exponentials, we recognize that this term right here is just equal to 2 times cosine of 4ka. Similarly, this term is equal to 2 times sine of 4ka. And then finally, this term is equal to 2 times cosine of 4ka. So what we actually have is 2 cosine 4ka times m squared alpha squared minus k squared h bar fourth subtracted by 4 ik h bar squared m alpha sine of 4ka. If I shove that in, then what we have now is that the magnitude of m22 squared is equal to m fourth alpha fourth at the front, and then subtracted by m squared alpha squared times, multiplied by this expression. So 2 cosine 4ka m squared alpha squared minus k squared h bar fourth minus 4 ik h bar squared m alpha sine 4ka, and then added with ik h bar squared plus m alpha squared times ik h bar squared minus m alpha squared. Or, sorry, wrong way around. It's, this is supposed to be a plus, and the minus is in front of the I. There we go. And then everything is once again divided by k fourth h bar eighth. Okay, at this point, let's see. What else can we do? Well, in green, this expression, this is really just equal to m alpha plus ik h bar squared times m alpha minus ik h bar squared, and then multiplied once again by another m alpha plus ik h bar squared times m alpha minus ik h bar squared. So immediately, these are just complex conjugate multiplications. So this becomes m squared alpha squared plus k squared h bar fourth times m squared alpha squared plus k squared h bar fourth. So if I plug that in, then I get magnitude m22 squared is equal to m fourth alpha fourth minus m squared alpha squared times 2 cosine 4ka times m squared alpha squared minus k squared h bar fourth minus 4 ik h bar squared m alpha sine 4ka, and then added with m squared alpha squared plus k squared h bar fourth, and then squared. And then everything is divided by k fourth h bar eighth. I'm sorry, I was looking through this and I just realized I made a very stupid mistake, which is that the cosines, or the sine term specifically, because in actuality, the relation is that e to the ix minus e to the negative ix over 2I is equal to sine x. So actually, in fact, there's supposed to be an I at the front of this. So that's my mistake. If I correct this, then there should be another I, so these two i's cancel. If there's another I once again, so the two i's cancel to a negative, and we're left with a positive. And that looks much more correct. So then we plug in everything as before, plus 4, and then get rid of the I as before. And at this point, the actual transmission coefficient is then just the inverse of this. So k fourth, h bar eighth, and then the underneath is going to be everything that we just wrote, m4 alpha 4 minus m squared alpha squared times 2 cosine 4ka m squared alpha squared minus k squared h bar fourth plus 4k h bar squared m alpha sine 4ka plus m squared alpha squared plus k squared h bar fourth squared. So sorry about that mistake, but regardless, we are done with this very tedious mathematical exercise, and along with that, we're also done with this problem.